Hey everyone, good afternoon. I hope I'm not the only thing standing between you and your lunch. But I'm going to be talking about ngrams today. We are going to go ngram hunting. And in a slightly clickbaity way, I'm going to try and tell you how we build search from scratch in-house at almost zero cost. So, starting with introductions, my name is Akshata. I'm founding product engineer at a small startup called Avon. I'm originally from India, but I've been in Singapore for the past 8 years. I worked at NAS Academy, Rakuten, and NUS before the startup. But the more interesting things to know about me is that I'm a complete hotpot buff. So if you're into that, Hari Leela just sent me a message that my points are expiring next month. Please get in touch after this. And I also have a legitimate license to design buildings because I'm a trained architect who got into computational design, loved the computational bit of it, and never looked back. So that's about me. What about the talk? Today I'm going to cover 6 bits for this talk. We'll start off with why search, which is sort of a common question, but okay. Then the main question, why did we do this in-house? It's sort of like reinventing the wheel somewhere. We'll go into search 101s a little bit, then we'll talk about indexing, go into ngrams, inverse term frequencies. We'll put it all together in an architecture that worked for us. And then I will hopefully leave you with some takeaways and some thoughts around this topic. So let's kick it off with why search. Search is invisible and everywhere. If you Googled something, you used search, which is obvious. I mean, you probably said Google it, not search it. If you used maps to get here, which I did, that was search. It actually went through all the possible routes and picked one that was most relevant for you. If you use ChatGPT today, that's also search. Out of all the text jargon that it could have thrown at you, it picked up the most relevant combination for you. And try and actually put together how many combinations of strings and letters it could have come up with to get to that little bit of text that made sense to you. Your brain is also search. You have all these ideas. I have all these words in my brain, and as I'm putting together words, my brain is actually rapidly searching through the words that would make sense to you. Sometimes my brain is slow, especially runs really slow on coffee, which it is right now. So if I don't make sense in some words, please forgive me. And where philosophically life itself is search, for me it is search for great hotpot. But anyway, we actually wrote a book about it, which I highly recommend. But let's go away from that. What I'm trying to say is search is important. But if you're still not convinced, 162 billion USD is the global search engine market size according to Business Research Insights in 2021. And I'm saying just global search engine market size. I'm not considering any of the other indirect applications of search. If you look at Google, it makes a revenue in trillion. Again, that's just Google, not Alphabet, the parent company. So even if you're not convinced that search is important, it's definitely profitable, which is why it's worthwhile to spend a couple of minutes learning about it today. So coming on to the context now, which is the startup that I work for. So again, I work for a startup called Avon. We are literally a 6-person company today. We got incorporated last year, and what we do is we build AI-based underwriting tools for financial institutions. Now, if you're not familiar with underwriting is essentially the term that you use to perform a function, which is figure out the financial risk associated with certain actions and take that risk for a certain fee. For example, if I provide a loan to you, I'm going to underwrite you, which is assess how risky you are. If you're a relatively safe person, I like your look, then yeah, maybe I'll give you $1,000 and I won't bother about it. But if you look shady, then my risk is high, so I'm going to charge you an interest for it. And by virtue of doing that, I'm underwriting you. Well, this is casual underwriting, but officially for NBFCs, financial institutions, underwriters are like Sherlock Holmes. Not only do they work with information that they are provided with directly by the companies who come to them for loans, they also work with a ton of external data to create a business risk profile for these companies. So these are people who are working with unstructured financial data. They are trying to identify financial relationships between the companies that they've been given and uncovering relationships that are not provided to them directly. And then they are trying to assess risk and fraud for the cases that they receive. So one very important thing in all this is getting easy access to all this relevant data in one place. Now what we built was an underwriting assistant, which is the AI tool that I talked about, and the underwriting assistant aids the underwriter to make these decisions quickly and easily, more accurately. So what this product, which we called Enrich, does is that it takes our financial statements, it runs an AI model on these financial statements, and it tries to put together a risk and consolidated business profile for the business in question. Now, these questions can be, what are the business health metrics, how are we predicting the future, what kind of loans does this company have, what kind of EMIs are they paying their salaries on time, are they paying their provident funds on time. And all of this requires contextual information being given to the AI for it to actually be able to come up with a very accurate statement. And this contextual information is what led us to consider a full text search for companies. Now we had all this data around companies, we got them from paid sources, public sources, government data, private data, but we needed it to be accessible, available in an API form for the AI model to consume. So basically what we were looking at is huge data sets. We were also looking at the cost because we are a startup. We couldn't afford to pay thousands of dollars on a search product, so the unit economics needed to measure up. And then we were looking at scale because this was being consumed by an AI model. To give you an estimate of how it worked is that, say somebody uploaded financial statements and it had financial transactions in them. A single financial statement upload could have over 90K transactions over 2 years, 3 years maybe. And each transaction would have at least 2 counterparties, which is to say 2 companies. So you're talking about 90 cross 2, which is 180K companies, probably less than that. But that number of companies for which you required contextual data at that point of time. And since this was a real-time assistant, we couldn't really expect the user to upload this and then go back and have coffee and come back the next day for the report. So we went back to the market and we considered market options. Elasticsearch was the main go-to, most obvious go-to, for good reason. We had Mongo Atlas, then we considered AWS OpenSearch, and we considered a new open source search engine that's sort of new in the market called TypeSense. And then we did the math. So Elasticsearch, when you're paying for a search product, you're essentially paying for 2 things, storage and compute. And for Elasticsearch, it did make sense because the storage, according to the kind of data that we had at that point, would have probably cost us about 30 USD a month. The compute would have been an additional 20 to 50 a month. We're looking at a fixed cost of about 90 a month. There was no serverless option, so we were committing to $90 a month. Elasticsearch was fine, we kept it on the side to consider it. We also looked at Mongo because Mongo Atlas did promise a serverless option. However, it was in coming soon phase, we didn't know how soon it would come. But on the other hand, the storage was pretty cheap. The fixed cost was about 58 a month. One restriction with Mongo though was the fact that for every index that you made, it sort of accrued towards an additional cost. So for example, if I went up to 10 indexes, I would have to pay for an M5 cluster, which is a pretty high tier in Mongo, and that means my compute cost would keep going up. For those of you not familiar with indexes, layman terms, for example, I had a company with 3 columns, address, name, and industry, and I wanted to be able to search by all of those. I would need to create 3 indexes to be able to do that. Then we considered OpenSearch. The storage was by far the cheapest here because we could leverage a free tier here. We had to pay a lot more for the compute though, which was a fixed commitment of 186 per month. It did have a serverless option, but that was null and void because the serverless option required a fixed commitment of 4 OCUs, which was coming up to 700 USD a month. So again, that never made sense. And then type sense, which seemed the fanciest and the coolest, but also was the most expensive at $730 a month for the configuration that we entered. So we thought a little bit about it. We were drawn towards Elasticsearch, but then one of us, I don't remember who, came up with the great idea of just build it ourselves. I mean, we're a startup, we have to do things like that, right? And we didn't want something exceptional. We just wanted something that worked, was cheap, and would help us iterate further and get a POC out. So we wanted to build it serverless, which means that we could control cost. Suppose the product tanked and bombed, then we could scale it down to zero, no fixed costs. We had control over the data and indexing, because if you've worked with financial institutions, the number of contracts they make you sign in terms of compliance is just crazy. So adding a third party would not be an issue. And then we had zero dependency on any other external providers. And finally, there was a geek factor, but okay, let's leave it out. So what do you do when you start thinking about building a search? And thanks to the long history of this domain, there was a lot to go out on. Google keeps telling you exactly what are the three components of this. Well, you start off with a query, you get relevant results, and then you measure the relevance according to ranking. Now, from the query to the results, what you need are search techniques or search algorithms. They can be as simple as having a linear search, a binary search, hashes, which probably most of you are familiar with. You can also have vector spaces where you try to plot every entity as a different vector according to different properties and then cluster them and get them out. You can make feature-based search, which is sort of what models do. And the best thing is that all of this is mostly openly accessible by virtue of libraries. So you have Lucene, Sphinx, Manticore, which are all open source libraries which provide search retrieval algorithms and different techniques free of cost for you to come, copy, leverage, use directly. Most of the search engines, software developer kits that are provided like Elasticsearch are basically built on these. But we basically came on this concept of ngrams and we were intrigued by it. So that's what we deep dived into. And what's an ngram? It's a very simple concept to understand. Long story short, you take a piece of text and you chop it up. And you chop the smaller the pieces, the better your accuracy. The bigger the pieces, the chunkier the pieces, less is your accuracy in terms of the kind of text analysis that you're trying to do. But you're breaking these text strings up to be better able to analyze them and form a picture around their context for it. So it's a technique that's commonly used for natural language processing, text analysis, computational linguistics, and it's also used heavily for information retrieval, which is what we will look at today. So how do you make ngrams? Like I said, you take a piece of text and you chop it up. And there are different kinds of ngrams that you can make. For example, over here, I'm trying to make wordgrams, and the first row basically shows you how you make a unigram, which means that I'm only chopping it up into one word per ngram. So from the phrase how to make ngrams, I get 4 ngrams or 4 unigrams. If I wanted to make bigrams, which is 2 words per ngram, then I would get 3 ngrams or 3 bigrams out of it. If I was doing trigrams, then I would get 2 trigrams out of this phrase. The count of ngrams is usually equal to the token size minus the ngram size plus 1. And you don't necessarily have to make ngrams out of words. You can make it with letters, you can make it with phrases. You can also do edgegrams, which is the second example over here. And depends on the way you want to use your search and the way you want to use this ngram. That's what decides the kind of ngram that you will build. For example, edgegrams are commonly used to do type ahead search, where you pretty much know what your beginning of the string is going to look like. So you want to like reference that beginning of the string as a fixed set and then reference the next documents from it. And from ngrams, I mean, it's a good concept, but then how do you use it for search retrieval? How do you use it for indexing? And the way to understand indexing is kind of like bookmarks. It's similar to the index that you find behind a book that you read. It's basically a cheat sheet or a reference that allows you to go back to original documents from pointers. So you can index via ngrams. So for example, I have a database and I have a column called name in which I have apple, pineapple, pen, referring to the nice catchy song a couple of years back. Say I have that and I want to index that via ngrams. So I'm going to take apple, I'm going to break it up into ngrams. For this example, I'm using trigrams. I'm going to put that trigram in an indexing table, and then I'm going to reference the document number as against that ngram. So say I'm looking at apple. Apple gives me 3 ngrams, that is 3 trigrams, app, ppl, and ple. That's the first 3 rows. And over there I can put in document number 1. That these are the 3 ngrams. That document number 1 is what holds these 3 ngrams. Now I come to pineapple. When I break up pineapple, I get another set of trigrams. Now if you see, pineapple and apple have a common apple. So the trigrams app, ple, and ppl are going to reference document number 2 also. Now every time that I search for anything with app, I'm going to get document 1 and document 2 returned for me. So I've cut down my sample set significantly like that. This is basically elaborating on that concept. So for example, I get a query called pinecone. I will break it up into ngrams of its own. I will go back to my search index and I will search for the ngrams that this query gets broken up into. For pinecone, that's pine, nec, and so on. I only have 1 ngram over here that I have in my index for the purpose of this example. So I go and find document number 2, which is pineapple. If you're getting pineapple for pinecone, okay, fine, reasonable search result, right? So this conceptually works so far. But the main question is, what about relevance? See, I search for apple. I'm going to get apple and pineapple both. How do I tell the user that apple is a better match than pineapple? And that's where we come to a concept called cosine similarity. It goes into a mathematical territory. And what cosine similarity is trying to do is basically map words as mathematical functions and then try to align them together to see if they are similar or not. That's the formula. It's kind of boring, but let's see it in action. So for example, I have a query called apple. I'm breaking that up into 3 ngrams, and then I get 2 documents, which is pineapple and apple. Pineapple gets broken up into 7 ngrams, apple gets broken up into 3 ngrams. Now mathematically, I can represent the weight of each of these ngrams as a vector, and when I look at it, that's PIN is basically 1 by root 7, INE is 1 by root 7, and so on. In terms of apple, it's 1 by root 3, and so on. Now, when I'm trying to compute the cosine distance between apple and pineapple, I am going to multiply the weight for APP of apple with APP of pineapple and get a product and sum that up to get my score. I can do the same thing with apple. Now the beauty of that function is if I'm doing it with the same word, I am going to get 1 because it's all going to map up. The bottom, the denominator is a square of the magnitude, the numerator is going to sum up to being the same, and 1 means you've got a perfect match. And everything else is going to fall below 1. And that's basically going to give you your relevance score. So great, we have a way to score that, but wait a minute. In our index, we don't have that. I mean, I'm only getting document 1 and 2. What do I do now? Go and look up the reference again and figure out what the magnitude and the vectors are? No. So here's where we try to play a bit smart. What we did was, instead of putting just the document ID, we put in the document ID with the weight and the magnitude of the significance of that ngram with that document. And then we would extract it and compute it directly within that search function when we were searching for something. Armed with that, we went in to try and create an architecture around it. And this is what it looked like. So we had a company service. It was running on AWS Lambda. It would talk to an Amazon DynamoDB database. It would go and update and populate our companies there. That would basically trigger Dynamo's DB streams or an event bridge, and then that would call an indexing service. The indexing service would then take those entities, chop them up, make those ngrams, make those indexes, and then we decided to save them in S3 because it was the cheapest by far. So we saved text files in an S3 bucket, and these text files were what we used in the search service to reference and then return the results for search queries. At the first go, what we indexed was 22 million company names. It generated about 400k ngrams, 393 to be exact. And we used an ngram size of 4. And this is what the distribution looked like. So you can see that most ngrams are pretty unique, which means that about 294k ngrams out of the 390k ngrams have only 10 documents or something. So if I can correctly identify the ngrams, I have a pretty good chance of getting what the user is looking for. There are only 11 ngrams which have more than 1 million documents. So distribution-wise, we were pretty safe and we were good on accuracy. Just for interest, this is the most frequent ngrams, which makes sense. You see a lot of enterprise trading, boring terms. A larger word cloud, anything larger than that, and my word cloud generators crashed. But yeah, it was interesting, made sense. This is what the company's naming ecosystem in India currently looks like. So we generated about 18 gigs of ngrams. For the first index storage, it cost us 4 USD. On a monthly basis now, it costs us 4 cents. For one query, we usually require reading 16 ngrams on average. Per query, including the lambda costs and referencing the ngrams, is about 0.00008 blah blah blah, which is essentially 8 cents per million queries. And let's revisit the math now. So as compared to the rest, this is what it looks like. We are spending 4 cents on storage, we're spending 8 cents per million queries for compute, and yes, we are serverless, we go down to 0. But there was a problem. This search, like my brain without coffee, was pretty slow. Well, not pretty, but it was slow. We were trying to do 200 queries per request, and what we were trying to get to was essentially 1 second response time. The actual time on production though was 5 seconds to about 20 seconds also. So 5 seconds we were still okay with, there was hope, but 20 seconds was just a no-no. And that's where we explore term frequency inverse document frequency as another concept. So what is this? Now, term frequency is, like the term says, how frequent is the term in the phrase that we're looking at. For a query, if I have apple apple, then APP is twice, divided by the total number of terms in that document. So it basically tells you how relevant is that term, how significant that term is for that particular document. And then inverse document frequency is essentially how relevant is that term across all the documents that you've seen so far. So if I have a term like enterprises, which I've seen in like 3 million company names, if I tell you enterprise, would you be able to find me which enterprise I'm looking for? No, you won't. None of these big words that you see, you'd be able to, you wouldn't be able to like use them for anything significant, even if you were going to like extract the ngrams from them. So we combined term frequency cross IDF. We already had a weight for term frequency in that cosine similarity function that we were using. We computed the inverse document frequencies. We stored them in a different document that was dynamically updated every time we made changes to the index. And now we had one additional step, which is once we broke down the query into ngrams, we would reference the IDF JSON to figure out which of the ngrams to discard. And then we would go ahead and only focus on the ngrams which actually made sense to figure out the search results that were relevant. With this, the 5 to 20 seconds went down to 3 seconds, up to 8 seconds. It helped us shave off a lot of the really time-taking queries because it removed the enterprises and those kind of limitations, I guess. And it was about 60% faster. But to be honest, it's still pretty slow in our opinion. It adds to the pre-processing step that the AI does. So We're still trying to improve it. We've played around with weights, other fancier techniques, and it's a work in progress. But so far, so good. It works. And now for the TLDR and the takeaways. So just a quick refresher, we learned about ngrams. Ngrams are essentially chopping up pieces of text. We learned about cosine similarity, which is basically a mathematical way to figure out whether two strings are similar or not. And then we figured out term frequency and inverse document frequency, which allows you to figure out whether a particular term is significant in a text, in a piece of string. But the big question still stands. Was it worth it? Because as a startup, you're pressed against the wall for innovation. You're trying to iterate pretty quickly, and what you want to do is stand on the shoulders of giants and not reinvent the wheel. We sort of tried to reinvent the wheel over here. So it did bother us. A lot of questions were around it. I would argue that it was still worth it. Because in terms of flexibility, we can use it with all kinds of data, even proprietary ever-changing data. We don't have to bother about adding more indexes. We don't add any additional overload for it. We have no vendor lock-in. The costs are minimal. Our recurrent costs are in cents. We can scale down to 0 or it can scale up to a lot, and we'll only pay for what we use. We actually made this product in-house, so we are trying to launch it for developers. In case any of you are interested, please do get in touch with me. But my main takeaway from this project was that it was a lot about experimentation and curiosity. It helped us build a deeper understanding of search as a domain, look under the hood for something that already exists, which is pretty common, and still question the basics. And what was mind-blowing to me was that a pretty simple concept like ngrams could be used, implemented for really cheap, and we got reasonable results. It's not like it fell flat on our face. It worked, and it works in production. So and that's exactly the kind of reason why I moved over from being an architect to engineering, and the reason I loved engineering for. So I'm going to leave you with this quote here. And the next time you see something that's invisible, maybe just look a little deeper into it and think, yeah, that's funny. In case of collaborations, partnerships, if you're interested, you can reach out to me at akshata@admin.finance, or you can also scan this QR code to reach my website, which also has a link to reach out to me. And that's going to be it from me today.
Yeah, I'm forced to use the mic. So, do you ever find out where the remaining 3 seconds to 8 seconds came from? Like, how will you optimize it even further?
Oh, the 3 seconds to 8 seconds was just with tf-idf.
Yeah, but where's the remaining latency coming from?
Oh, where's the remaining latency coming from? It's still coming from trying to get all these ngrams and process. Oh, sorry. It's still coming from trying to get all the ngrams and processing them. Yeah. We've tried to play around with weights and trying to shave off the number of ngrams that we fetch even further. No luck so far.
So you mentioned that it was pretty cheap to host, but given the amount of time and engineering that you put into, is it really worth it in the end?
That's a good question, and that's actually the argument against doing this in-house, because it took a significant amount of engineering effort. I was working on it full-time for like a month or something. You have to look at the long-term versus short-term, right? Like now we have this productionized and everything. We don't have to look at search again, apart from trying to optimize it. As opposed to maybe putting it $60 to $90 per month. If we stick to that, that's for 2 years also. That's 90 cross 24 already, right? So maybe it would pay for it. But yeah, that's a valid point.
Any more questions? Okay, behind. I'll chase down you guys. Come.
Okay, so one thing I can't quite grok is the decision to use the cosine differences, because based on my understanding, I think one of the advantages of cosine differences is that there's you can put a semantic weight on each characters and how important it is. But since you're breaking your ngrams up into character level, why not something much faster like a Levenstein distance?
When we took the cosine difference, we were actually trying to weight it out. That's what we tried first. So the initial ngrams were weighted higher than the next ones. We tried to come up with a list of words that would score less, and then that was also accounted for. But the weight kind of turned out like cancer a little bit in the initial indexing, so we threw it out, and this worked better.
I'm gonna take one more question, two more questions. So I'm gonna go to the back.
So just like search, what other areas of your business are you trying to implement in-house versus relying on different providers?
I'm so sorry. I have one mic. It's only my mic working.
You're getting a good workout. The AI model we are trying to build from scratch. That's a headache, but also a good chase. That's actually the most significant part of the effort so far.
I think there's only one question left, right? You're the last question. Cool. One more, okay.
Can I ask why you consider vector databases instead of this ngram thing?
Why didn't we consider it?
As in like what? Do you like consider vector databases and why it's not suitable for this application?
I think it's a buzz thing in like AI right now, right?
Yeah. We did consider it. This talk is actually one of 3. So you should see something around vector databases in the third bit of it. And it is relevant. It's not like it's not relevant. It's not one over the other. This was just part of the process.
Last one? Okay, last one. We've got 2 more. Okay, one, 2. Okay, the reason why I'm taking so many questions is because like after this is lunch, so.
Hello everyone. So I have a question, like you are looking for the words and the words are present in the documents. So the words, so what's the relevance of it? Like, so let's say I'm searching for Apple, so you have like thousands of files which contains Apple. So you'll give me the documents relevance to me, like document 5 is containing Apple and then document 10 is containing Apple.
Correct.
Is it like that?
Correct.
And then how does it help you? Like, let's say I have Naveen is working in Singapore. Like, if I add that phrase, will you be looking at this kind of phrase in the overall document and then you will get it? So is it that way you are building this product?
Yeah, correct. I will take your query, I'll chop it up, I'll try to look for documents that match most closely with your query. I'll give you those documents back. Sure, the search service will only give you the indexes of the documents. There'll have to be another service that fetches the exact documents and shows it to you. But yeah, it's like a back reference.
Okay, thank you.
Do you want to take another one?
Sure.
Okay. It's you, right?
Thank you. I want to ask, in order to shave time, have you considered even like more simplistic options, like based on popularity signals? Because people will not search this whole thing. There will be popular results that people will consider. Would you actually like see, okay, these are the top occurrences, and then like most recently searched or top results, and then just pull from that list first, so that you can just theoretically cut your time. Yeah, that's a very good suggestion. Thank you for that. It's being currently used in an automated fashion by the AI model itself, and the AI model tries to like pick the top 3, the top 1, and then use it in the processing step next, right? We do have some functions on the front end that allow the user to change what the AI model has picked. We don't actually incorporate that feedback back into the search service yet, but that's a great suggestion. We would definitely look into that.